Okay, here we are, final unit, Unit 4, Electrochemistry. So this is Section 1, Lesson 1. We're going to define oxidation and reduction. So here we go. This material is dealt with on page 712 to 716 of your textbook. There's a few practice problems here, and we've got a couple images here. We've got Leo and Mervyn. Now, the oxidation and reduction has nothing at all what to do with Mervyn. But Leo, he's real important here because Leo is an ox, and that's going to make sense to you now in a few minutes. We also have this Hibernia platform here, and this is an oil rig, and that's going to have some meaning as well. All right, so remember Leo, forget Mervyn. Here we go. Okay, here's the outcomes for this lesson. We're going to look at oxidation and reduction reactions, and we're saying that an oxidation reduction reaction are specialized reactions that involve the transfer of electrons from one species to another throughout the chemical reaction. And these chemical reactions are going to become real important, and we see them around us all the time in terms of our cell phones or iPods, anything that takes a battery, a rechargeable battery, the car battery in your car. All of these particular reactions are chemical reactions that involve a transfer of electrons. And what we like to do is harness or control these electrons as they flow and get these electrons to do work for us, like, you know, a speaker, the energy of a speaker, or turn on a light bulb, or spin a motor, or something of that nature. All right, so we're going to try and capture these electrons. And not all chemical reactions do that. So we say that if we're seeing a transfer from electrons from one species to another in a chemical reaction, we have to specify what's going on here. So we're going to refer to the species in the chemical reaction that loses electrons as the one that's going to be oxidized, and the one that gains electrons in this chemical reaction is going to be the one that's reduced. All right? So a loss of electrons is oxidation. Gaining electrons is reduction. In this case, what we're looking for is the idea that we can't have one without the other. It was kind of like the Bronsted-Lowry definition of acids and bases, wasn't it? In order to have an acid, we had to have something that was going to donate a hydrogen. In order to have a base, we had to have something that was going to gain, because the physicists didn't really like the idea of a free hydrogen floating around. Well, the same sort of principle is going on here. An electron really not going to be able to exist on its own. It's a really hostile environment out there. And if we had something that was oxidized and would lose electrons, now you're saying, well, there's an electron floating around out there. And as soon as that electron gets produced, what's going to happen is immediately something is going to come along and gobble it up, and that something is going to be reduced. All right? And the idea behind this, of course, the very, very tiny electron with its negative charge, man, it's just not a good environment to be an electron out there. So instantly it's going to be transferred from one to another. And we looked at this, and this is why Leo is an ox, is because Leo, loss of electrons, is oxidation. Easy enough. Leo is an ox. The ox business is going to come later on. Well, we know Leo is an ox. The OX stands for oxidation. So Leo is an ox. And if we look at the other picture that we had, we could look at oil rig. And what we're saying with oil rig is oxidation is a loss of electrons. Reduction, rig, is a gain, R-I-G. So that's a way we can remember what's going on here. Okay? And again, the redox reaction, so we put reduction and oxidation together, hence the term redox. It's simply an electrochemical reaction, something like happening in a battery that's producing electrons, and the electrons are being transferred from one species that's oxidized to another species that's reduced. Okay? And there we go. And we said, don't confuse this with acid-base reactions. I've seen multiple choice after multiple choice where they simply refer to a redox reaction as being a transfer of protons. Redox is a transfer of electrons. Bronsted-Lowry equations are transfers of protons. A proton is a hydrogen. This guy up here is an electron. Two different things. Electrons are negative, protons are positive. There we go. So do not confuse with that. And maybe we can put a nice big Sasquatchy type footnote here. So that's a footnote. Another left footnote. 4 toes this time. Okay. So we want to be able to see what's going on here with, say, some kind of chemical reaction. So we're looking at this reaction. We're saying, is this your redox reaction? We really can't see any electrons moving from one to the other. Not like with acid-base chemistry. We could actually say that if something was to be an acid, it was going to be a donor of a hydrogen. So therefore, anything that was an acid had to have that hydrogen there that was easy to donate. So we could actually see if something was going to be an acid. But in this case, we really can't see what's going on here because we don't see the electrons. So what we have to do is we're going to look at this simple redox reaction and say, well, let's draw a Lewis dot diagram and see what's going on here. So what we're seeing is that sodium in group 1 has 1 electron, and chlorine in group 7 has 7 electrons. And what's happening is because this guy has an electronegativity very, very, very low, the electronegativity of sodium from the periodic table is 0.9, very weak. That electron is not held on very tightly, so what happens is, as soon as something comes along that wants to pick up an electron, sodium gladly says, "Boy, take it. I don't want it." It gives it away, right? It donates an electron. It becomes oxidized. The chlorine has a very large electronegativity, and you can see that one on the periodic table. It has an electronegativity of 3.0. The highest is 4. So chlorine has a very strong attraction for electrons. So as soon as the sodium gives it away, chlorine picks it up. So chlorine becomes reduced, right? Rig, reduction is a gain of an electron. Leo, loss of electrons, is oxidation. So what we end up with is sodium loses an electron, so now it becomes positively charged. It lost the negative. And chlorine, because it picked up that extra electron, now has an extra, it has a surplus. It has more electrons than it came with. So now it's leaving with a negative charge. So we can see that the sodium changed, it lost an electron. The chlorine changed, it gained an electron. Do we actually see the electron transfer? Absolutely not. We see the result of the electron transfer. It's the formation of an ionic compound here. So we're showing that. Now you might say, well, sir, something's not right here. Well, how come you got 2 chlorine here and there's 1 there, and we balance the equation? How come this is not showing that? Well, the idea behind this is that chlorine at standard temperature and pressure is a gas, and it exists as a diatomic gas. That's how chlorine is comfortable. And the reason for that, of course, is it makes a bond with itself, something like this, where it would share an electron. But when it comes in contact with something like sodium that wants to give away an electron, these 2 chlorines go their separate way, and they try to form a bond with the sodium here, an ionic bond. Now what's going to happen is, because I've got 2 chlorines now, I'm going to have to bring in 2 sodiums. So I'm going to have 2 sodiums that are going to donate these electrons. So what we want to be able to do is show you the transfer of electrons. I'm just going to get rid of those 2's there. I'm going to show you this through an equation format where we're saying sodium is losing an electron to produce a sodium ion. So that's oxidation reaction. The chlorine is gaining an electron. There we go. Let me just fix that up there. It's gaining an electron. As we said here, it gains an electron to produce Cl minus. There we go. Now the problem is we have to try and balance this, and because we've got 2 chlorines, that we need 2 electrons because we need 2 chlorines here. So I'm going to have to bring in 2 electrons. So I'm going to change that 1 to a 2 there. Now I'm going to say, well, where is it getting the 2 electrons from? We can't have 1 electron in one equation and 2 in another. It's got to be a transfer. If we need 2, then something has to give up 2. If we only have 1 to give up, that means we have to bring in twice as much sodium. So I'm going to multiply the top equation by 2 and say, yeah, there we go. We got equal numbers of electrons. So for every 1 molecule of chlorine, I need 2 atoms of sodium. And then we balance the equation. Do we see the electrons? Absolutely not, because the electrons are on opposite sides here. They should always cross out and balance. They're being transferred. They're like an intermediate type thing, although not intermediate because they don't exist there, and it's simply being transferred from one to the other. So what we say then is that this guy right here is an oxidation half reaction, and this is a reduction half reaction. So this equation here is showing me 1/2 of what's going on. It's showing me 1/2 of the transfer. This reaction here is showing me the loss half of redox. This guy right here is showing me the gain part of redox, right? So we see half reactions, and that's what we refer to them as. Okay. What we want to be able to do here now is say, okay, if we get a chemical reaction, we want to be able to easily see what's gaining or losing electrons. We want to get rid of any of the riffraff, so to speak. We want to get rid of any of the spectators, anything that's in a chemical reaction that's not necessarily involved in the transfer of electrons. Now, what do you mean by that? He says. All right, well, let's do an example. We're going to do a reaction of solid zinc with some aqueous solution of copper 2 sulfate. So I'm going to take a piece of zinc, and I'm going to dip it in a solution of copper 2 nitrate. Now, what I want to do is I want to write the word equation for this, because I want to be able to write these equations saying zinc reacts with copper 2 sulfate to produce copper and zinc sulfate. Okay, good enough. From that, I can get a balanced total non-ionic equation. There's no ions here. What we're saying is zinc, copper 2 sulfate. Now, there's no 2 here. That refers to the charge on the copper, right? Copper 2 plus and sulfate SO4 2 minus produces copper metal and zinc sulfate. Okay, what we want to do here now is we want to write what's called the net ionic equation. Now, the net ionic equation is telling us put everything in the state the way they exist in the solutions and whatnot. So in this case, we're saying, well, what do you mean by that? Well, zinc solid is zinc solid. It's like a galvanized nail or something like that. It's a chunk of zinc metal. Copper sulfate, because it's aqueous, what this is telling me is that it's an ionic compound that's dissociated into its ions. So in water, it doesn't really exist as CuSO4. It really exists as free-floating copper ions and free-floating sulfate ions. Likewise, copper is going to be a chunk of copper, copper solid. And over here, we're going to see some zinc sulfate AQ again, which means it doesn't really exist as ZnSO4. It really exists as free-flowing zinc ions and free-flowing moving sulfate ions. So anything that's AQ is going to be dissociated. Everything else stays the same. Solids, liquids, gases stay as they are. It's only the AQ ones that are really formed from ions. So what I'm going to do is I'm going to rewrite this and say anything that's AQ, I'm going to write it in its dissociated form. Everything else that's solid or gas or liquid, I leave it as it is. Okay? What I'm going to do now is I'm going to say, well, we know that zinc was a metal, and when the reaction took place, it turned into an ion. It's a different species. And I know that copper is an ion, but after the reaction, it turned into a solid. Sulfate didn't really change. So sulfate is one of these spectators that we're referring to. They're not involved in any of the change. It didn't change. Sulfate stayed the same. So what I'm going to do is I'm going to say that guy is simply in the way. It's a spectator. Its only job was to bring copper ions into the test tube. Its only job here is to try and help balance out the zinc charge afterwards to keep it electrically neutral. So it really doesn't play a role in the chemical reaction itself. So what we want to say is, well, what really changed here? And what really changed was the fact that zinc reacted with copper ions to produce copper metal and zinc ions. So what's going to happen here now is the chunk of zinc that we threw in the test tube is actually going to start to turn orange in color. So the copper is going to start sticking on. It's going to turn black and orange and really yucky because the copper is starting to stick onto the zinc. And then the zinc ions are going to be filling up the container. We won't see them because they're colorless. So what we're saying then is, well, what really happened here from the change of electrons? Well, we're seeing that the zinc solid, in order for zinc to be forming a 2+ ion, it had to get rid of 2 electrons, right? 2 plus, 2 negative, they cancel out for a 0 charge on each side. So zinc was losing electrons, so it was oxidized. And likewise, the copper must have picked up these electrons. Copper 2+ plus 2 electrons produces copper metal. So this was the reduction half reaction. All right, so what we're seeing is the electrons are taken care of. There's no surplus, There's the same number of electrons being produced as being consumed. We don't see them because we can't see electrons, but we know that the transfer happened because the zinc changed from a 0 state, no charge, to 2+. It lost 2 electrons. The copper went from a 2+ charge to no charge by gaining those 2 electrons. So in other words, this up here is showing me information that I really don't need. All I'm interested in what's going on between the zinc and the copper ions. The sulfate was not involved in this transfer of electrons whatsoever, so we'd refer to that as a spectator. Do we need it? Well, not in the redox reaction, but we need it in the overall because we have to somehow get copper ions into the test tube, and that's its purpose, right? Okay. Here's another one. All right, well, this is the exact same thing. I'm just rewriting it again on the other side. Okay, so that's what we just talked about there on the other side. Okay. Now, what we got to look at here is we're going to say, yeah, okay, so zinc was oxidized and copper was reduced. But we want to look at this and say, from another perspective, we're going to say, okay, if zinc was oxidized, what encouraged it to lose its electrons? Because it's just not going to lose electrons for no reason at all. There has to be something out there that's going to attract these electrons and take them away from zinc. And we would refer to that as the agent that would have facilitated the oxidation process. So we would call that the oxidizing agent. All right, so it's the agent or something there that's going to encourage the zinc to give up its electrons. So we would say that the zinc was oxidized by copper 2+. So even though zinc was oxidized, we say that copper 2+ was the oxidizing agent. That was the species that encouraged zinc to give up its electrons, an oxidizing agent. Now, in this particular example, the oxidizing agent itself is the one that gets reduced. So in this case, copper 2+ was reduced, so therefore it's the oxidizing agent. Similarly, we might look at it from the other perspective and say, well, what encouraged copper to want to gain electrons? In other words, what encouraged copper to be reduced? Well, that would have been what we refer to as the reducing agent. What's causing the reduction? And in this case, what's causing the reduction is zinc. Zinc is the one that wants to get rid of these electrons. So zinc is encouraging copper to absorb or take these electrons. So it's the reducing agent. Playing with words, playing with words. Okay? So generally speaking, what we should be asking ourselves is, if we're asking you which one was the oxidizing agent, we're saying which one was reduced. Okay? So because copper was reduced, copper 2+, copper 2+ is the oxidizing agent. It was reduced. And if we say which one is the reducing agent, we're saying, well, which one was oxidized? Zinc was oxidized, therefore it's the reducing agent. All right? So what we're saying here is if something's going to be oxidized, what is out there, what agent is causing the oxidation? And if something is going to be reduced, what agent, what species is causing the reduction? So play around with those words there. Do a few examples. See if you can get. I'm going to do another couple here for you. All right, here's a reaction where we want to write the net ionic equation for the reaction of magnesium with aluminum sulfate. And we want to list all the reducing agents and oxidizing agents and the species reduced and oxidized. So here we go. We got magnesium solid reacting with aluminum sulfate AQ. It's a solution. And in this case, what's going to happen is a single replacement. So the aluminum and the magnesium switch places, and we get magnesium sulfate. Anything that's aqueous, we dissociate. So we write the dissociated total ionic equation. And we're saying, okay, can we cross out any spectators? Absolutely. In this case, it's sulfate again. It does not change. Same thing before and after. What we do then is we would rewrite the net ionic equation. So this is magnesium solid reacting with aluminum ions to produce aluminum and magnesium ions. Okay. What we do now is we say, okay, what really changed here? Well, the magnesium turned into magnesium ions. In doing so, it released 2 electrons. So we can say then that the magnesium was oxidized. It loses electrons. On the other side of the coin, the aluminum went from 3 plus to Al solid. It gained 3 electrons. It picked up the 3 electrons that it was deficient. So we can say that this guy was a reduction of electrons. Now, what we need to do here is we got to look at this and say, hold on, no, we got different numbers of electrons. So what I need to do is somehow balance out these electrons. So I say, I'm going to multiply this equation by 3 to get 6 electrons, and I'm going to multiply this equation by 2 to get 6 electrons there. So what I would do then is I would rewrite my equation, and then I would cross out my electrons to show that all the electrons are being transferred. And there we go. So the overall reaction would be 3 magnesium metal reacts with 2 aluminum 3 plus ions to produce 3 magnesium 2 plus ions and 2 aluminum. So what we're seeing here is, we got different numbers of atoms here, but it's not the atoms that we're trying to balance in terms of the magnesium and aluminum. It's the number of electrons that we're trying to balance out here. We have to have the same number before and after. So looking at this in terms of oxidizing agent and reduction agents, we're looking at this equation saying, okay, magnesium was encouraged to lose its electrons. What made magnesium lose its electrons? Well, it was the aluminum ions. So in this case, even though magnesium was oxidized, the aluminum would be referred to as the oxidizing agent. Okay? And in terms of the aluminum wanting to gain electrons, what made aluminum want to gain electrons? Well, it's the fact that magnesium wanted to get rid of them. So even though aluminum was reduced, the magnesium was the reducing agent. Okay, and you can see that it was oxidized, therefore it's the reducing agent. Aluminum is reduced, and therefore it's the oxidizing agent. Okay. Here's another type of special redox reaction. This guy's called disproportionation reaction. And this is a case where one species can actually have a dual role. Okay, it can be a double agent. It can be the reducing agent, and it can be the oxidizing agent. So a double agent, working for both sides here. Now we've seen something like this when we talked about acids and bases, didn't we? We looked at a species that was referred to as amphoteric or amphoprotic, in its ability to be an acid and donate a hydrogen, and ability to be a base and accept a hydrogen. Well, in this case, we're not talking about hydrogens, we're talking about electrons. So we're looking at a species that can be oxidized in one step, but it can also be reduced in another. And copper 1 plus is one of these species that can do that, because we can show that copper 1 plus can lose an electron to become copper 2 plus. That would be an oxidation half reaction, and at the same time we can show copper 1 plus gaining an electron to becoming copper metal, and that would be reduction. So what we're seeing here then is that both of these roles is taken on by copper. So copper 1 plus is oxidized, so that makes it the reducing agent. At the same time, copper 1 plus is reduced, which makes it the oxidizing agent. So it's a double agent. And we see the same sort of thing here with mercury. And exactly the same type of process here, mercury 1 plus going to 2 plus, and mercury 1 plus going to mercury liquid. And we can see that takes on 2 roles. Okay, so that's a basic introduction as to what oxidation reduction is. So what you guys have to do is try some of these problems here in your textbook and see if you can identify which is oxidized, which is reduced, and then identify the oxidizing and reducing agents. And remember, Leo, he's an ox. Oil rig. All right, forget Mervyn. All right, good enough. We'll talk to you later. See ya.